Hello, it's lovely to be back with you all. It's lovely to see so many of you back in the room. And I know that you've been battling with a very late night in some cases, or jet lag in some cases, but we're nearly there. We've got a couple more sessions of very important speakers, and then we are going to wrap up with some exciting news, of course, from Larry. He's going to talk about the Startup Support Programme, and then we'll have, of course, closing words with Catherine Hadler. So this session, we've got 4 speakers, and we are running ahead of time. Thank you, Aidan. Infrastructure and supporting technology, and the first speaker is Emma Cooney from ESRIC, and she's going to talk about something which Bernard alluded to in the first panel of this week, Space Resources Week, Europe's largest dusty thermal vacuum chamber. So please welcome her to the stage.
Thank you very much, Lisa. I am Emma Cooney. It's a pleasure to be here with you all today. I'm an engineer at ESRIC, and I'll be presenting the latest on the DTVC project, which is ESA's project, and the DTVC will be hosted and operated at ESRIC here in Luxembourg. So let's jump in. The background of the DTVC project centres around ESA's strategy for in situ resource utilisation, for advancing exploration of our moon and building up testing capabilities in Europe to progress this. There are lots of thermal vacuum chambers in Europe of sizes up to many metres in diameter for testing components, subsystems, and even entire spacecraft. However, facilities are limited in Europe for testing the interaction and impact of lunar dust in a lunar relevant environment. Developing components, instruments, and subsystems that can maintain their performance in the dusty lunar environment is a key challenge to going back to the moon. Lunar regolith is so adhesive, abrasive, and invasive. So with support of its member state partners, in collaboration and in workshops and consultation, ESA identified the scenario 3 in terms of size and capabilities as largely closing this testing technology gap that existed. A consortium led by Spartan Space with support of Hawks Life Support, Mana Electric, and ESRIC LIST is bringing the DTVC to Europe. Let's take a look at the specs. So the chamber's internal diameter of 2.5 metres and internal length of 3.5 metres is able to accommodate payloads of varying configurations. It has a staged vacuum system to reach 10 to the minus 6 millibar with regolith in the chamber. Temperatures can range between minus 180 degrees C and plus 160 degrees C, according to lunar night and day extremes. It includes fully automated control and monitoring with multiple sensing of pressure and temperature in the chamber. And there will be a viewport and camera with a lighting system for remote monitoring and recording inside the chamber during tests. For connecting to subsystems and supporting testing and research, there are multiple spare flanges for feed-throughs for power, instruments, control, data, and gas sampling. The new DTVC also features a special hatch design to enable future retrofitting with solar simulator. So the vacuum system, here's our DTVC from the back, or bulkhead end. Just one more click. There we go. The vacuum system, designed by Manna Electric, includes 3 stages. The first stage uses rotary vane primary pumps to bring the pressure down to about 10 to the minus 1 millibar. This requires very special control in order to avoid this boiling effect where if the pressure comes down too fast, we get a boiling of the dust or regolith simulant, which can end up heading out of the chamber, and we don't want that to happen. So the automatic control system, as well as the system itself, is designed to avoid this. In addition, there will be special dust traps and filters should any of the dust leave the chamber. In the second stage, turbomolecular pumps bring the pressure down to around 10 to the minus 5 or 6 millibar. It's a 7-stage kinetic pump operating at about 30,000 RPM. The cryogenic stage is the third stage, where the gas molecules are condensed and frozen and absorbed onto the cryogenic surfaces. And after this stage, there'll be few gas molecules left in the chamber. We're looking at 10 to the minus 6 to 10 to the minus 9 millibar, depending on regolith or clean conditions inside the chamber. Okay, so the thermal system, here's a cutaway of the inside of the DTVC. And you can see that there's a thermal shroud inside. 2 large liquid nitrogen tanks will feed liquid and gaseous nitrogen into the building to supply the thermal management system to regulate the temperature. The thermal system, designed by Hox Life Support, includes several shroud sections that line the inside of the chamber, and liquid or gaseous nitrogen circulate inside tubes within the shrouds to maintain temperature set points before being discharged. So in the new DTVC, interaction of lunar dust on the test subject will be possible from above and below. The dust dispenser assembly is made up of 6 dispenser units, each of which delivers fine dust via a motorised shaft and brush system. The motor can be started and stopped at discrete time points. Surface and subsurface interactions with lunar dust can be tested. Tests can include up to 400 kilograms of lunar simulant. And this system is being designed, or has been already designed, by Spartan Space. Same with the transporter. Spartan Space has designed a purpose-designed transporter to ensure safe and effective transfer of the payload tray and the dust dispenser system into and out of the DTVC. It features a variable height telescopic mechanism with guide rails and rollers, locking points, and safety latches. So I'll show you a typical thermal cycle of a TVAC system, a thermal vacuum system. The hardware or subsystem is subjected to a number of hot-cold cycles in a vacuum environment. This is simulating lunar night and day temperature extremes. The subsystem's performance is verified through comprehensive functional tests, which are carried out under these extreme thermal conditions. Here we see the extended capability of the DTVC, again showing thermal cycling under vacuum conditions, this time with the dust dispensing that can be programmed to operate at discrete time points throughout the testing campaign, sprinkling fine lunar regolith onto the subsystem. And in this next slide, it'll just give you a better picture of the typical testing sequence inside the DTVC. So here we have a subsystem that has been prepared and is ready for testing. The test cycle has been programmed and the control system computer is ready to execute. The DTVC is prepared and regolith simulant is deposited in the dust dispensers and onto the payload tray. Using the transporter, these are transferred inside the DTVC, and regolith simulant dust is now shown here as yellow balls. The subsystem is brought into the DTVC and set up for testing. All connections are made, sensors are ready. Firstly, the system is depressurized, and that is using the 3-stage vacuum system. When high vacuum is achieved, the thermal management system kicks in, bringing the temperature up to the set point. As temperature holds during dwell time, the dust is dispensed automatically. And this continues after bringing the temperature down in the chamber, and the cycle goes on so that the impact of thermal vacuum on the hardware can be evaluated. And this allows for measuring impacts on self-cleaning systems, optical and thermal systems, rotary and sealing systems, repeat exposure, and other critical testing. There's still time to come to ESRIC's booth and check out our model of the DTVC. It's a near replica in 1:20 scale. We've also prepared a flyer with technical specifications. Feel free to take one, or just get onto our website where you'll find those technical specs to download. And finally, our DTVC will be hosted in a new space campus building, thanks to LIST and the Luxembourg government, project managed by Fond Belval. Our building design has dusty and clean areas, separated by airlocks to contain dust and provide a controlled environment for safe working conditions. ESA and NASA have provided very helpful guidance to ensure this facility is fit for purpose. It includes a large external building to store regolith simulant, spacious working areas for staff and visitors. So it's scheduled for installation in 2026 and should be available, our DTVC, later next year for research and testing. We really look forward to welcoming researchers and industry partners and commercial users. We're working on a specific engagement plan for our customers, so if you're interested in booking time, please get in touch with us. And we hope to collaborate on many projects with our space resources community in the future. Thanks very much.
Thank you, Emma. Do we have any questions in the room for... yes, we do.
Thank you. Aaron Shamati, my question is about the dispenser system. Is it some kind of rotation system combined with the sieve system to ensure that below one dispenser the dispensing is homogeneous, or is it a different system? Because for me it was not entirely clear from the presentation.
Your question is the dust dispensing system
yes.
operating in a...
Yeah, the operation itself.
Yeah, the intention has been to make it as uniform as possible
yes.
across the subsystem.
And the principle of the working method is some kind of rotary system with a sieve or something similar? Or?
Something similar to a sieve,
okay.
Exactly, yeah, and it's...
Just because I was wondering about the clogging.
Yeah, and that's all... part of the development has been to minimise the clogging and ensure that the distribution is repeatable over several times during a testing cycle. So that's been part of the development by Spartan Space.
Okay. Thank you.
Yeah, I can't tell you because I didn't design it myself, but that has been a specific aspect that has been critical to the design of their system.
Okay, thank you.
Thank you. I've got 3 more hands, so if you keep your hands up, we can see where to bring the... Thank you.
Thank you. Jakub Ciążela, Mirrores. My question is about the type of regolith that you will use. Will you use different types, or will you focus on lunar maria or maybe highland regolith? Could you give some hints on that?
Thank you.
Yes, so the intention is for different types of regolith to be able to be used within the DTVC. The development has been made with EAC1, local European available regolith, but certainly other regoliths can equally be used inside the chamber.
Another question here.
Hi, thank you. Is there a capability for hot fire tests inside the vacuum chamber and evacuation of engine exhausts in real time?
Currently, you would have to, probably check that out with the designer, but there should be an intention for hot fire testing. Not entirely sure if that's a capability, but I'll check it out for you, so get in touch.
Thank you.
Hello. Thank you, Emma, for your presentation. My question is regarding the vacuum system, and I was wondering if you have any data on the vacuum system, the pump down curves, and also what would be the threshold when you introduce the outgassing materials into the chamber?
So the vacuum system has been designed by Manor Electric. It's not yet tested with the chamber itself. The chamber is still under manufacture. However, the design intends to meet these very low pressures. Of course, the time taken to meet the different pressures after each stage will depend a lot on how much outgassing needs to happen. We intend to thoroughly dry the regolith, for example, to ensure that we're not outgassing moisture for hours upon hours.
Thank you. We have another question here. Then I know there's at least one more question. Thank you.
Hello, Severin Luhr from Fibercode. I was wondering if the regolith particles can be electrically charged to simulate the moon environment before they are dropped or while they are dropped?
Currently, the electrostatic charge capability is not included within the DTVC design itself. However, in the future, this is one of the capabilities that has also been identified to be potentially retrofitted to the system. Thank you.
I think the last question.
Hello. Thank you for the presentation. My question is, when you have reached vacuum operation with the cryogenic cooler, do you actually stop the turbopump or do you leave them on? Because from my understanding, turbopumps aren't really friendly with particles. So I was wondering if they risked any damage from the regolith.
The system should be pumped down, and then it should not be necessary to continue running the turbo pumps, if I understand correctly, if there's someone from Mana Electric here. There is very little opportunity for the regolith to be sucked out of the chamber once the vacuum level is below about 10 to the minus 1 millibar. So for those two reasons, I think it's been well de-risked in the design of the system.
Thank you very much to Emma. Thank you, Emma. Thank you. I can see we have some more people hovering at the door. Please feel free to take a seat if you wish. We have plenty of spaces here, in the front row, over there. Take your pick. I quite like the central front row seat. It's always very nice for our audience. And don't let me scare you off by saying that. Next up, we have Christopher Ogunlesi from ESA. He's going to talk about ESA's Vulcan Analog Sample Facility Applied Simulants Research. So please welcome Christopher to the stage.
Hi. Yes, my name is Christopher Ogunlesi. I am a research fellow working at the European Space Agency. Particularly, I work in the Vulcan Analog Sample Facility in the UK. And today, I'd like to give just a brief overview of the history of Vulcan, what it is, some of our past work, and how we might be able to work with you in the future. So, as I was saying, just to give a bit of background on Vulcan's history. So it started in 2014 as a collaboration between the Natural History Museum in London and the European Space Agency, where its main goal was to act as a geological repository. This contract then eventually expanded to include a database of simulants as well as some analytical equipment, before eventually in 2018/2019 that contract ran out and the sample was moved from the Natural History Museum to its current location in Harwell, which is just outside Oxford in the UK. Thanks. Yes, just outside Harwell in the UK, so just outside Oxford, where it's affiliated with the ESA site there, EXAT, and its name was changed from the Sample Analog Curation Facility to its current name, the Vulcan Analog Sample Facility. Now, I'm going to be talking about analogs a lot, so I'd just like to clarify what I mean by analogs, because in the space context, analog can really mean one of two things. You can either have analog sites, which really concerns itself with locations, so it's where you could have analog missions or rover testing, for example, and then you have analog samples, which really concerns itself with simulating extraterrestrial materials. And it's these analog samples, particularly soils, which Vulcan concerns itself with, although we can supply soils or simulants for analog sites and also advise on analog sites. Now, to go to what the actual purpose of Vulcan is. Vulcan's primary aim is to conduct simulant-based research as well as technical activities, and then to apply our geoscience expertise in order to de-risk future exploration missions, particularly in the context of future in-situ planetary surface exploration. And to do this, we've kind of divided our purpose into these three core tenets of support, improve, and inspire. So by support, we really mean that we aim to support users of simulants, and that for that we really need to understand what the needs and requirements are and then work with them. To improve, we hope to improve confidence in the European simulant landscape, both from a user perspective as well as a supplier perspective. And then inspire, we hope to inspire the next generation of planetary geoscientists through our intern and graduate trainee programs, as well as our numerous outreach activities. So just to go back to our research. So our research is really divided into three core themes. So you have European analog landscape. For this, I mean landscape in the figurative sense. We really mean what's going on in Europe in terms of simulants. So that could be who is developing them, what analog sites are there, or what technological activities are going on that require simulants. Then Moon-Mars analog development, it's exactly what it says, but also concerns itself with things like sites such as the lunar facility, which I'll go into in a bit more. And then solar system analog studies, for which I mean not only development of simulants, but also scouting locations and sites which could be potentially used as sites for Moon, Mars, or other planetary bodies. So I now just want to focus a bit on some of our previous work. Just to clarify, I was not particularly involved in some of these, so if you do have questions on these, I can try and answer as best as I can, but I may direct your question to a colleague of mine, May Martin, who's also here. But yes, just as an example, so I'm sure you've now all heard lots on the Prospect drill, but for those unaware, Prospect is an ESA package that's going to fly on Intuitive Machines 4, consisting of the Proceed drill and the Prosper sample facility. For this, the drill itself will drill about 1 meter into the lunar surface, collect samples, and those samples will then be transferred to Prosper, where they'll be heated up, where they can analyze water and other volatiles that come off. And for this, in 2019, Vulcan was involved in the initial drill tests, for which we supplied about 200 kilograms of lunar South Pole simulants, as you can see in the image there. And then samples collected in this drill test were then sent back to Vulcan for analysis and curation, which you can see in the photo on the bottom. We were also involved in the 2019 ExoMars field test, or ExoFits, which occurred in Tabernas, Spain, as well as the Atacama Deserts. And for this, Vulcan was involved in the design and development of the field test, which included location studies, as well as sampling procedures development. Now, as I said before, we were also involved with the lunar facility. So the lunar facility, for those that don't know, is ESA's Moon analog facility, located just next to the Astronaut Center in Cologne. It is a facility where it has 2 chambers containing over 900 tons of lunar regular simulants, and it can be used for mechanical testing, rover testing, or astronaut task simulation. And it consists of 2 chambers. You have the main chamber, which you can see on the right, but also consists of a smaller dusty chamber, which contains about 20 tons of lunar Highland simulant. And it was this that Vulcan was really heavily involved in the initial selection and characterization of that. So just to go into that a bit more. So as well as needing to consider things such as key characteristics of the simulant, such as particle size distribution, shape, morphology, etc., we also had to take into consideration things like production and delivery costs and lead times, supplier location, as it had to be somewhere within Europe, and things like that. So after narrowing that down to a few select simulants and suppliers, we then worked with European industry, particularly the Norwegian Geological Institute's X-ray Mineral Services and Petrolab, to follow and design a strict characterization path flow, as you can see on the right there. And following that led to the down selection and eventual selection of a particular simulant, which here you can see is Lumina 250, which comes from a quarry in Greenland. Now, I mentioned that our third tenet was to inspire the next generation, so I just want to talk about a couple of the intern projects that we had running over the last year. So first of all, this was the Argonaut Regolith Interactions and Simulant Experiment, or ARISE, where the goal of this was really to investigate how rocket plume exhaust can scatter regolith over the lunar surface. But the novelty of this came from the fact that it was really looking at 2 locations in the lunar South Pole where there could be potential future Artemis landings. And in order to develop this simulant, what they did was that they focused on 3 characteristics: the modal mineralogy, the cohesivity, and the bulk density of the simulants. These things are the main things that affected the plume surface interactions. And then through a combination of simulation and experimental work, they tested this or investigated this. And the experimental work was they took a small vacuum chamber, filled it with the simulant, and then 3D printed a rocket nozzle there. And then by allowing air in, we're able to simulate rocket exhaust, as I think you can see.
3, 2, 1.
Yeah. Exciting. Yes, and then the other intern project was the Martian Advanced Regolith Simulant for Iron Extraction, or MARSI, where the goal of this was really to aid in de-risking and advancing future exploration activities, particularly focused on iron extraction. For this, the reason why they wanted to do this was because, again, although there have been many simulants focused on Martian regolith, there have been less that have been focused on specifically for iron extraction. And for this, they focused on data gathered from the Perseverance rover in the Jezero crater, and they were able to come up with a simulant for which all oxides were within 5 weight% of data from the Perseverance rover, as you can see in that graph in the bottom. Now, just to focus very briefly on some of the current work that we do. So we have a graduate trainee working with us, Danielle Vosper, who couldn't be here, but she's developing 2 simulants, one for the Martian moon Phobos, another one for the asteroid Psyche. For the Phobos simulant, she's really doing that to de-risk the IDEFIX rover, aim for the MMX mission. And for Psyche, she's developing a simulant to aid in de-risking future asteroid mining and ESRIC opportunities. As for myself, I focused more, as I have a background in material science, focused more on additive manufacturing of simulants and other ESRIC activities, really focused on things like bulk characterization, particularly in low gravity environments, as well as additive manufacturing of reduced regolith. And just to focus a bit on Vulcan's future to end with, our immediate short-term goal is to become a center of expertise in our geological and planetary science activities, and we hope to, in the very short term, actually become a curation facility for some extraterrestrial samples, as well as generally expanding the facility. But generally, just to say in the end, we are exploring other research avenues, and we have many collaborations that we're setting up. So if you're at all interested in using simulants or require advice, please contact us. And yeah, contact details there. So thank you very much.
Thank you very much, Christopher. Thank you. Any questions for Christopher? I don't think I see any hands. You were so clear. It was all so... Oh, sorry, we do have a hand up. You've got to be quick.
Thank you. Jakub Ciążala again, Mirrores. My question is for Psyche simulant. What is the metal content there? Is it 80% as predicted from modeling, or you went for something else?
So that's currently being worked on by our graduate trainee, Danielle Vosper, who's not here. I can give you her contact details later, where she'd be able to fill you in more, but I am not certain, to be honest.
Okay, I will be grateful. Thank you.
Thank you. Any other questions? You were just too clear. Thank you, Christopher. Thank you very, very much. Thank you. So now, thank you. We have Hemanth, who is going to talk about versatile architecture of the ground-based pilot plant and utilization plant. So please welcome to the stage Hemanth Madakashira.
Good afternoon. Hemanth Madakashira. I'm a team lead at Space Application Services. What we do mid-size system indicators. And in the perspective of lunar economy, we are involved in gateway projects. We are working in Argonaut, which is a European lunar lander. We are working on several rover concepts. One is a commercial one, and the other one is the ESR rover, one of the ESR rovers concepts, and it's called LPSR, Prospecting and Scouting Rover, lunar. We are also involved in several ground operations that includes both software and also the control centers, and also involved in the ESRIC activities, and that's the reason I am here. We also have an experimental facility called Ice Cubes at ISS, inside ISS, and also we closely work with Japanese entities for any payloads that require external ISS environment. We also have a small subsidiary in US, Houston area, and we would like to grow our business in US, but due to nasty political scenarios, currently that's, the process is going on slower pace. Okay, let's now jump into the ground-based pilot plant. So, what is the vision? The vision of the ground-based pilot plant is to be a world-class innovation center, interacting with the international ISRO community, and also addressing sustainability aspects, such as recycling and recouping of energy, and support development of future missions, such as lunar pilot plant. And the main functionalities of the end-to-end functionalities of the ground-based pilot plant includes processing of regolith, that includes sieving, magnetically separating, or electrostatically separating, making pellets. It could be sintering. It could be also consolidating by just external brutal force, making some pellets, all of those. Plus also the oxygen or alloy production, which includes molten salt electrolysis process. Once we have off gas coming from the reaction, we need to sort, store, and refine the products, and as well also byproducts, so that we can feed into the system and analyze it for the future purpose. Plus, we also want to address sustainability aspects, such as recycling waste, or recycling the carrier gases that we have, and also recouping the energy itself. And the goal is to provide an open source platform that performs not only nominal operations of a pilot plant, for long duration operations up to 10 years, but also provide an opportunity for international ISRO community and also research institute and commercial companies to integrate their technology. It could be right in the form of a small sensor to a subsystem that we have currently seen today. It's a lot of presentations, and all of those technologies can be included, such as fuel cells. It could be sintered blocks, or it could be a regular transportation system, or some kind of a sensors. So the objective of the pilot plant is to demonstrate long-term operations, learn about at the pilot plant scale, learn about the long-term operations and the implications of it, and try to apply for the future missions, like, as I said, the lunar pilot plant, and also facilitate or act as a test bed for any new technologies that we think of that could interact with the ISRO processes. So, during the phase 1 or the initial phases of the study, along with the needs from the agency, we have performed a survey and collected additional needs from stakeholders. That includes both ISRO stakeholders and also non-ISRO stakeholders. And then this information is structured in R&D agenda that we provided to the ESA, and this is composed of several research topics. That includes not only scientific development topics, but also technology development topics. We have collected about 64 different topics that, and we would like to address all of these topics or scientific agenda, investigate them during nominal operations of pilot plant, and as well as address them through open calls to the industry. So we classified the plant into 2 segments, the pilot plant. One is called core GPPP, and I think I have a old presentation here, but maybe I'll just. I think it's still old, but I'll just go ahead with. So I'll just go ahead with some talk. Sorry. So we have classified the plant into 2. One is a core GPPP, which includes essential functionalities to really produce oxygen and metal alloys, and also extend the core process using additional functionalities that may assist, that may boost the end-to-end process. The end-to-end process includes right from preparation of regolith until the processing of regolith, processing of the products and byproducts, and also recycling aspects, sustainability aspects, and all of those. And these end-to-end system also covers the R&D agenda that was in this slide, and also potentially plug in new technologies into the system. Also simulate, also add some simulations and perform hardware in loop testing, and also collect the data over the time, and potentially use this data for the digital twin models, and also test technologies along with other facilities that this facility will be located next to, mostly which is a DTVAC. And this gives an opportunity for the technologies to raise their technology readiness level and try to qualify for a space environment or DTVAC environment. So I'll just go through the presentation in a different slides. Bear with me because this is not updated version, by the way. So we went through the preliminary design and we don't know where to start with. So we want to start with the known values, which is ISG value, which is a global expression roadmap. So we need to produce 45 tons of oxygen per year. And for the pilot plant, we consider about 450 kilograms, which is 1/100th of the scale. And we consider several lunar conditions. One is polar, and another one is non-polar. And we took out different operation conditions and then what production rate that we need to produce for the pilot plant. And there are two options here. One is a near complete reduction, that is complete entire regolith, produce oxygen and as well as metal alloy. The other one is very fast, which is only partially reduced reduction. And we want to have a near complete reduction because we don't want any regolith in it and want to separate again. So we want to go with near complete reduction and have a batch size more or less closely fixed towards 7.5 kilograms per batch of regolith. So we filled in regolith 7.5 kilograms of regolith per batch. So I will try to skip this slide because we have only a minute to go. So I will jump on one of the important slides, which is the development and utilization. So you can talk to me on the technical aspects later on, but the development, we have three different streams. Development of plant itself, operations, and utilization. They three run in parallel with an offset and they synchronize. So we are at the leftmost area. We are doing the feasibility study currently. We are proposing some kind of de-risking activities for the key technologies, mostly for the process, the electrolysis process. And we will propose a kind of development plan, costing, and strategic planning that will feed into, that we provide to ESA, and ESA will modify and feed into the central of ministerial. This is the first one. And then the short term is to produce the core elements. I talked about core elements, which is more about oxygen and metal production. Sorry. And we have de-risking elements, and then we do integration at ESRIC. Simultaneously, we would like to have a test plan and as well as run these operations together with the new technologies, utilization aspects. We would like to have international ISRO committee to participate, provide their ideas, have the contracts, and implement into the core elements, update the test plan, and extend the complete pilot plant, which is the core elements to other elements, and then input to the lunar pilot plant, the study of lunar plant, because we know what it takes to run a pilot plant for longer time. We learn through it, we iterate to lunar pilot plant, and potentially repurpose GPPP to lunar pilot plant at the end. So that's it. My apologies for overtime.
Thank you. Thank you.
I made it short presentation, but this is not the original one. This is the old one, so.
No worries. Do we have any questions?
please.
The exhaustion. Oh, we have a question of last night is catching up with them.
Sam Hemanth with Astroport. On the intake with the regolith, is the pre-processing the regolith part of the system, or is it you just going to receive pre-processed regolith from whatever source? In other words, are you going to, the granularity of the grains coming into the system, you just going to take it from some already source that's already been pre-processed and then it goes into it, or are you using that pre-processing technology as part of the system?
Yes, these are part of the system. So this is a system of interest, the key ones. It all revolves around the electrolysis. If the electrolysis requires some kind of a pre-processing, then we have to go with the pre-processing. Sometimes the electrolysis require a condensated block with a defined porosity. So we need to achieve this using some subsystems, which is in the pre-processing step here, which is part of it. We could start with the commercial equipment, but then we should try to make some equipment very specific for the plant.
Thank you.
Thank you.
Any further questions? It's the post-lunch lull. Thank you very, very much. Thank you. Thank you. So one more talk before you can recaffeinate quickly and return to the room. And it's Aude Vignelles from AROSE. So this is a talk entitled ROSE Oasis, Operational and Systems Interoperability Site, a Lunar Proving Ground. Please welcome Aude to the stage.
Thank you. I'm Aude Vignelles. I'm the former Chief Technology Officer of the Australian Space Agency. No, it's not an Australian accent that you hear, but I am a proud Australian. I'm here working and representing AROSE, and we are going to talk about OASIS, the Operation and System Interoperability Site, a Lunar Proving Ground. So who is AROSE? AROSE is a consortium, an industry-led consortium of 15 members. AROSE was non-for-profit, very, very important. AROSE was actually founded by Pamela Melroy, who spent a couple of years in Australia before becoming the deputy of NASA administration. So we were lucky to have her for a couple of years. She was the first one to realize that the expertise, the experience, and the skills that Australia has in remote operation had a direct application for space. I have to say, the first time I visited a mission control center of a resources company, and that was Rio Tinto in Perth, I wasn't expecting that. And sometime I thought, I took a wrong door. I must be in the Johnson Space Center or in NASA JPL, because it's very similar infrastructure and operation tasks. I had a great discussion with the drilling operator who was there, and she was doing not one, not two, but 12 operations of drilling 2,000 kilometers away in the Pilbara region. And when you think of this ratio, one operator operating 12 assets, when you have a rover on the moon or on Mars, you usually have one asset and up to 100 or 200 people controlling that asset. So that was interesting to look at that ratio. And she was walking me through the fact that they have a user interface that takes into account the delay, the latency. They're using geosynchronous satellites to control this, so all that is taken into account. And at some point, she had an expression. She looked at me and said, I could be drilling on the moon, no difference to me. And you're like, of course, there is so much to do there. So AROSE is really between the translation of industry, the resources sector with the space sector, and the translation between two domains, the space sector and the terrestrial sector. So what are we talking about when we're talking about space operation? We're talking about big things. We are not doing the Apollo missions anymore, which were short duration and couple of tasks and not so much ground covered. Also the lunar rover that they had, I think they covered up to 30 kilometers during Apollo 17. But we're talking about big things to build on the moon for a sustained presence, which is still the plan, I hope. Well, we want to build landing pads, we want to build roads, we want to build communication infrastructure, PNT infrastructure, power infrastructure, big surface, long duration, a complex architecture, systems of systems. And all these things are going to be built by different space agencies, by different industries, by different countries, and all this has to magically work together. So this interoperability and this integration of system is very important, and we're going to have to test this somewhere on a large scale. What are we talking about when we're talking about terrestrial remote operation? Well, this is not too different to the previous picture. Well, it's red dirt, before it was gray regolith, but we have the same activities. We have the remote drilling, we have the remote trucks who are carrying some dirt from A to B, we have processing plant, we have communication, we have power, very similar. And when we look into the, you will recognize the icons there for the Moon to Mars architecture. You can put each of those, communication, infrastructure, power, mobility. You can put all these icons on that picture and the previous pictures as well. And I'm sure all of you working in different companies, you can put your logo in some of these activities there. So I'm sure you're going to be very interested in being part of this next picture, which is how the remote operation sectors in the resources sector are testing, validating, certifying their operation before deploying that into their real sites. So this is the ARP. We love acronyms in space, but in the mining sector as well. It's the Australian Automation and Robotics Precinct. This is a site that exists today. It's a permanent, dedicated site for the resources sector to test their assets and their operation before deploying that in the field. So you have a map of the different areas. You have an areas to test your drone, you have an areas to drill, you have an areas for your remote trucks, you have an area dedicated to different activities. On the top left, you have MDEX. They are the world-leading companies for remote drilling. So they are testing their drilling operation, making sure it's safe, because the resources sector has two main concerns, and a few of you have presented and talked about this today and yesterday and Monday as well. The safety and collision avoidance are the two main concerns of the resources industry, and I think we are sharing the same concern when we are thinking of big operation on the moon. In the middle picture here, you have some integrators company like Hexagon. They're buying assets off the shelves. They are customizing them with sensors, and then they want these assets to work together. So they are doing integration testing on these sites to make sure that everything is done safely, because sometimes you have human in the loop, and we're going to have astronauts in the loop at some point, and want to make sure that all this is going to work fine all together. You can see in the bottom picture, so this is 51 hectares, which we've been challenged at how many cricket fields, how many soccer fields does that represent? So that's 71 European football fields, 1900s tennis fields. I don't remember cricket fields, but that gives you the ideas of the size of this, and it can be expanded. There are some permanent infrastructure there, so you have offices, you have a warehouse where you can prepare your assets, you have a big auditorium, you have a private LTE there, you have fiber, you can fly drones, and we are talking with ACMA, which is a ITU body in Australia, to see if we can have S-band, X-band, terrestrial line of sight, and you can drill. And you can do whatever you want with the ground, which is something very unique, I understand. So when we saw all that, we were like, this is really the place where we can also do some space activity. We've tested this concept in Colorado Springs. We talked with 6 agencies, 15 companies. We're going to update this because we've talked with a lot of you Monday, Tuesday, and today. We've already had a lot of new information and new ideas and new use cases. So we're really excited to continue the discussion. But the people who are interested are, again, the agencies who are designing all the architecture, we're going to have to build on the moon. The industry is going to have to deliver this infrastructure, and the industry and the rovers are going to use this infrastructure. So everybody is interested, and this is not competing with any existing site. See, we talked with DLR, who has this Luna site in Cologne. We also talked with NASA and ESA and IOAG, which was a very interesting conversation. We are not planning of reproducing the regolith. This is not the goal of this site. This site is to test your CONOPS and to test the terrain. It's not to test how am I going to interact with the regolith. The discussion with Logic was very interesting. So Logic is born from the ESRIC consortium, and they're really looking into the operating guideline for infrastructure and interoperability of infrastructure on the moon. And they came up with this lunar proving ground terminology. And when we pitched them Oasis, they said, this is the first lunar proving ground we are seeing, and we're just starting the conversation with them. Very quickly, this is the main feedback we got so far, and really looking forward to hear more of you during the break or after. Again, permanent dedicated site. You don't have to go super far away in the middle of Tenerife or Canary Island or whatever. You have to go today to do your analog testing. It's 40 minutes away from Perth, so you can sleep in a bed at night. You don't need to be far away with nothing. It is safe. It's large scale again. We can really do your 10 days operation. End-to-end testing, not just one specific activities, which is what are the current testing facilities are offering you today. You can just test one task. Here you can really do the end-to-end mission. Customizable terrain. If you want us to dig a crater that looks like wherever you're going to land on the moon, please let us know, and we can make that happen. And there are a lot of people who will be very happy to try to reproduce some crater on the moon. Safe, secure, available comms. So there is already private LTE available there. We are looking at SX, K-band, or whatever band you want us to look at. PNT is there. We can also simulate the lunar orbiter. We're going to give you a PNT position and have drones simulating that. The model is infrastructure of a service. Today you rent a shaker table or a dirty TVAC. It's going to be the same service. We are also thinking that you don't need to come with your asset. You can leave the asset with us, and we can set it there whenever you want, and you can test it from wherever you are. This global cross-sector is very interesting, and sometimes we are thinking, going to do a challenge. Day one is going to be space sector, solve the challenge. Day two is going to be resources sector, solve the challenge. Day three is going to be debrief, who did the best in which challenge. And I think with this collaboration, this is where you drive innovation, this is where you drive the standards. And I think whoever wants to be part of this is a very strategic positioning. Super quickly, because I can see I'm over time. These are a couple of use cases, example. First example is really easy. You're having your rover on the site, and you're operating for 10 days, and you're making sure that your mission is successful. Every time I ask a rover operator, what is your worst nightmare? It's like, when I think my rover is here and is actually there. So come and test it again and again and again, and train your operator as well. This is a perfect place to do that. Any lander who's going to have a lot of rovers and payloads to offload on the moon, and how they're going to operate after that. That's another interesting use cases. And then you can think about, we were talking about 26 missions between now and 2030 on the moon. It's going to be a lot of rover all over the place. How are we going to make sure that the rules of operation are working fine? And we had a lovely chat with Arti from UNOSA, who was really interested to see how far we can bring this. Lunar mission, traffic coding, management, fault simulation, the list goes on and on and on, and we are really looking forward to talk with you about what are your requirements, what are use cases, and on your way to ISC in Sydney in September, October, please stop by Perth. On your way there or before coming back, you can have a tour there. We can take you to the mining site, and you can have a look for yourself. Thank you very much.
Thank you. Thank you so much, Aude. Do we have any questions for Aude? Yes.
Coffee time? Oh, no.
Yes. Yes. We got coffee.
Bjørn Elseth from Norway. Have you have any contact with
energy companies, for instance, in the oil and gas sector? And do you think there is additional benefits working with those kind of actors?
Well, yeah, absolutely. I think the space sector has a lot to learn from the resources sector, but the resources sector understand as well that by working with the space sector, they're gonna improve efficiency, drive innovation, and for them, any opportunity to innovate, to do things different, so they can be more efficient, safer, and more resilient, and more performance, mean they're gonna make more money and be good for their business case. So they're very interested in this cross collaboration, and this is something unique that Australia can offer. Because again, 25 years of doing remote operation, no other country can offer that expertise and that background.
Thank you. Any further questions? Well, thank you, Aude. Thank you so much. I think you rightly said everybody's in need of a coffee. Thank you for the wonderful presentation. Another reason for everybody to book their tickets to Australia for September. With that, we have a coffee break and we will start again in the room at 3:30. Thank you very much.